Hello and welcome to Chapter 8. We're going to talk about additions, reactions to alkenes today. So the functional group that we just made in Chapter 7 in elimination reactions, we are going to carry forward and see what those beautiful carbon-carbon double bonds can do for us. I really like this table in your textbook. It gives you that nice flow of this chapter, and we are going to follow this flow as well. So as we start off, we'll see today a couple of thermodynamic considerations for all of our addition reactions. We'll kind of do a summary of everything in terms of substitution, elimination, and addition, and then we'll be able to start with our hydrohalogenation reaction. We'll go through a couple different hydration reactions during our time here in Chapter 8. We'll then go to hydrogenation, halogenation, halohydrin formation, and dehydroxylation or dihydroxylation. So when we're looking at all these types of reactions, again, what we are adding is going to be very dependent on what the reaction name is. So we have some reaction names this chapter. You don't need to memorize the name, but what would be helpful is knowing the reagent that has those addition substances. Notice here what is highlighted blue and red, and then be able to work with that type of a reagent and say, well, what kind of a reagent is it? Does it go through a carbocation? Is this a concerted reaction? Things that we have seen before. They might look slightly different here in the addition because of the type of reagent we have with that alkene. But we're going to have some fun. So patterns with pi bonds. What I want to start us off with is just this idea that pi bonds we haven't really worked with yet. Maybe resonance, but that's pretty much it. Pi bonds can act as a base and as a nucleophile. It's dependent on what they are attacking. So we can think about them as being a base when we do a proton transfer. And that is usually when the other component with that pi bond is an acid. Notice HA here is an acid. We'll still need our beautiful, wonderful pKa's to be able to understand when that reagent is a good acid. The pi bond can also be a nucleophile, though, and it can do a nucleophilic attack when presented with an electrophile. We spent a lot of times with electrophiles in the last chapter, so we'll see a couple of new ones in this chapter as well. Types of reactions. We've seen substitution and elimination before. We're just going to go through some basic thermodynamics before we get into our actual addition reactions. I like stepping back and seeing the three types of reactions that we have: substitution, elimination, and addition. All of our reactions will fit into one of those three categories. So reminding us of what a substitution reaction entails, it's one sigma bond breaks and one sigma bond forms. So it's a replacement of a carbon leaving group bond for a carbon nucleophile bond. Typically, these reactions were exothermic, and the delta H was essential, or delta S was essentially zero. So we see that the enthalpy is the driving force for this reaction spontaneity. An elimination reaction was when we had two sigma bonds break and one pi bond form. So we see a beta hydrogen and an alpha leaving group are going to be removed and a new pi bond is formed. Typically, because sigma bonds are stronger than pi bonds themselves, these reactions are generally endothermic. And why we see that is because we know that the sigma bond itself is much stronger than the pi. The direct overlap of atomic orbitals is more stable than a pi. However, they're very small endothermic magnitudes there. The delta S is positive, and that's what overall makes these reactions favorable. When we think about how many reactants and how many products we have, we typically see a reactant that's an electrophile with a base, 2 things on the reactant side, and 3 things in the product side, the alkene, the conjugate acid, and the leaving group. So there is usually an increase of entropy. And so elimination reactions are going to be really, really similar to our addition reactions. They're exactly opposite. An addition reaction is going to be 1 pi bond breaks and 2 sigma bonds form. What we'll see is that that pi bond is going to break and add across that pi bond X and Y. We're going to see a variety of different X's and Y's here. Typically, these reactions are exothermic because of the addition of 2 new sigma bonds to our organic molecule. But again, we're bringing 2 molecules together to be more structured. And so we usually see a decrease of entropy with these. So you can think elimination is opposite of addition, right? But we'll see a variety of different types of addition, not just ones where we add an H and a specific leaving group. We will start with something that's very similar to what we've seen before, though. All right, so the first one that we're going to see is the hydrohalogenation reaction, which is a pretty good opposite of the elimination we saw in chapter 7. Now, typically, when we see elimination reactions, sometimes we saw heat involved with those. That was looking primarily at the idea that in an elimination reaction, entropy is favorable, so we want to crank up the temperature with that. Addition reactions are usually at low temperatures or room temperatures because entropy is unfavorable. Remember, addition reactions have a delta H that's negative and a delta S that's negative. So we'll think low temp for these to be really spontaneous. Elimination reactions were the opposite. Endothermic, but increasing in entropy. And so these tend to be high temp for these reactions. We didn't focus too much on those, but we do want to be able to understand some and hang on to some of our thermodynamics as we move forward in our specific reactions. So hydrohalogenation is going to be an addition of HX across that pi bond. Notice here HX can be chlorine or bromine, so HCl or HBr. You can use HI, that's totally fine too. That's a very reactive acid, but it still will work. HF is not highly utilized since HF is a very weird reagent. The pKa, remember, of hydrofluoric acid is 3.2, so it's not the best acid in the world, and it's just one of those reagents that you need special certification to handle, and so we don't often see it presented simply because it wouldn't be something you were presenting, would be presented to you in a organic chemistry undergraduate laboratory. All right, let's get into our reaction. I always like to start off with the curved arrow mechanism of a general reaction. Notice that there's a carbon-carbon double bond here. I'm going to label this as alpha and beta just because that's something that we remember. And so we'll see 2 arrows occurring in this hydrohalogenation reaction, but they are going to be stepwise. So I'm going to write the mechanism right down here. And again, this is going to be just a generic stepwise reaction. First step, proton transfer. Our alkene will react as a base. What that will do is it will put the hydrogen on one side of the double bond and put a carbocation on the other. We also make X minus. Notice in this reaction, I have created something that now is sp3 hybridized from an alpha carbon that was sp2 hybridized. Our carbocation, our beta here, is still sp3 2 hybridized in this reaction. Nothing has changed for that beta at the moment. First step, proton transfer. Second step, nucleophilic attack. So what we will see is that we are going to be getting H and X added across that double bond, alpha and beta. We go through a carbocation intermediate. Very important to be able to walk through these two-step reactions because it will help us understand some of the regioselectivity of this reaction. Hydrohalogenation is regioselective. Why? Because we will always favor the more stable carbocation. So let's get into that real quick as we scroll up to identify a couple of specific things in this mechanism. I'm going to start off with this alkene. Now we are going to be able to see the regioselective nature given a specific alkene and a specific acid. First step, proton transfer. Now, where would you like to put your hydrogen? And where would you like to put that carbocation? A good rule to remember from way back in chapter 6 is that the carbocation is more stable on a more substituted center. So if we look at the difference between how I labeled alpha and beta here, alpha has 1 carbon group coming off of it, beta has 2 carbon groups. So when we think about which carbon is more suited to hold the positive charge, beta is more substituted, it is more stable at that position. If you wanted to think about putting the alpha as the carbocation, remember that a secondary carbocation is not as stable as a tertiary carbocation. And so looking at this is the regioselective nature. This is not observed because the carbocation will always choose to go on the more substituted position. It's more stable there. So the actual transition state of that first step, the proton transfer, which is our rate determining step, will be more suited to become a tertiary carbocation than a secondary. Br minus can then come in and do a nucleophilic attack. So there is our only product. H was added to alpha. Halogen bromine was added to beta. Just a quick reaction coordinate diagram here before we move on. 2 steps, reaction progress on the bottom. Let's just call this energy on the Y. We'll start with our reactants. Remember at that first step, we are talking about forming a carbocation intermediate. The tertiary carbocation that we formed is the most substituted and the most stable. If you wanted to think about where that secondary lies and why we don't see the less substituted carbocation form is because the activation energy for that forming that secondary carbocation is way too high in energy. This is why we do not see a secondary form when a tertiary, a more substituted carbocation is available. And then products. Beautiful. 2 steps, reactants to products. We usually see, again, exothermic reactions for this. Because the transition state here for that rate determining step is close in energy to the carbocation. Remember the Hammond postulate said If you have a endothermic reaction, that transition state is closer in energy to the carbocation. Therefore, the carbocation is influencing that that choice, right, for the activation energy, that choice for the first intermediate. So we will always form a more substituted carbocation when available. This is called Markovnikov addition. Markovnikov addition is the idea that the carbocation intermediate will always be the more substituted. Because we are going through a carbocation intermediate, the bromine will add to the more substituted position. Of the carbon-carbon double bond. Don't just memorize that this always happens. It always happens with hydrohalogenation, but it doesn't always happen with other reactions. Now let's just think about that transition state really for the proton transfer. Why we see the carbocation is influencing is because as this pi bond is breaking and trying to form a bond with the hydrogen, we are already starting to feel that delta plus on one of the two carbons, alpha or beta, one of the two carbons of the carbon-carbon double bond. And so as that hydrogen is being picked up by the alkene in the proton transfer, we also have to consider the carbocation being formed. So that carbocation plays a huge role in understanding which position gets the hydrogen and which position gets the halogen. There are ways to mitigate that Markovnikov addition, right? If we think about alpha or beta, 1 or 2. Numbering or naming is really, really important here just to be able to visualize where things went, especially since our hydrogens kind of get lost in our skeletal structures. So in Markovnikov addition with using HBr or HCl addition to a pi bond, we go through a carbocation intermediate. And so that is Markovnikov addition. The hydrogen will always get attached to the less substituted side. The halogen will always get attached to the more substituted side. Anti-Markovnikov addition is a very interesting mechanism. We will do this mechanism when we discuss chapter 10. It is a radical intermediate, which is different than a carbocation. We actually get a completely different mechanism when we add in peroxide. ROOR is a peroxide. When we do add the peroxide in as a reagent, we get a radical reaction, and that actually ends up with an anti-Markovnikov addition, where the halogen gets added to the less substituted position and the hydrogen gets added to the more substituted position. This does not mean that all of a sudden carbocations don't mind being on the ends or being on less substituted positions. Note, it is a complete change in the mechanism. We will only be working with the Markovnikov addition of hydrohalogenation at this time, but we will revisit the anti-Markovnikov addition in chapter 10. So we said that our reaction of hydrohalogenation was regioselective. The region at which the carbocation gets placed is very specific, and therefore the halogen gets placed on that more substituted position. But remember, when we have a carbocation, that we have a top and a bottom side. I really like this diagram to be able to say that hydrohalogenation is not stereoselective. There will be all types of racemic mixtures. If we make a chiral center, we will get both R and S. Think about our substitution unimolecular reactions, the SN1 reactions, where we had a top side attack and a bottom side attack. That same thing happens here. When we have that nucleophilic attack from the halogen to the carbocation, the halogen can attack on the top side or the bottom side. We will always get a 50-50 racemic mixture if we are making a chiral center. Let's just take a moment to practice with a reaction one last time before we end today, or end this reaction. So when we're looking at addition here, pi bond breaks, proton transfer, we are going to put the hydrogen on the less substituted side, which is carbon 1, and we'll put the carbocation on the more substituted side, which is carbon 2. Cl- is formed, and then we'll do our nucleophilic attack. And when we form that new carbon-chlorine bond, what we notice is that we indeed made a chiral center. So what that means is that we will get two products, one with the chlorine attacking from the bottom side, and one with the chlorine attacking from the top side. No other carbon was changed, so notice that extra methyl group that was wedged at the beginning is still wedged at the end. So we make enantiomers or diastereomers depending on what our molecule looks like, but we will make all possible products when we attack in this reaction, because a carbocation has a top and a bottom side, so therefore we will make multiple types of stereoisomers. Again, regioselective Markovnikov addition always for us when we add a HBr or HCl to an alkene, but not stereoselective. We'll get racemic mixtures when possible.